So let's use this algorithm to go through and prove some things about the integers. And this extended Euclidean algorithm, and specifically the guarantee of the existence of these Bezout coefficients, is going to be what allows us to do a lot of the cool things that we're going to be able to do with the natural or the integers. So if a, b, and c are positive integers, such that the greatest common divisor of a and b is 1, so these are relatively prime, and a divides b times c, then we can say with definitively that a divides c. The proof of this is very straightforward. The GCD of a and b is 1, and by Bezout's theorem, there exists S and T such that this value, the GCD of A and B, is equal to S times A plus T times B. So we have the equation that there exists S and T such that S times A plus T times B is equal to 1. If we multiply both sides of this equation by C, we get that S times A times C plus T times B times C is equal to C. And by our theorems from modular arithmetic, we can show that A divides C. Specifically, A divides T times B times C, because by assumption, I should write this down, we're assuming that the GCD of A and B is 1 and that A divides B times C. So because we're assuming that A divides B times C, from the theorem that we proved in the first lecture on modular arithmetic, this means that A divides any integer times B times C. Specifically, A divides T times B times C. And it's clear that A divides S times A times C because we have just an integer multiple of A. And because A divides this term and this term by the previous theorem that we also proved on adding divisibility, we have that A divides S times A times C plus T times B times C, which means that A divides C, completing the proof. Now, this theorem is really cool for a number of different reasons, but it allows us to do some really neat stuff. Specifically, I'll give you an example, or rather a non-example. Suppose that we want to express that a congruence 14 is congruent to 8 mod 6. This holds and is valid, but what's not valid to write we divide by 2 and write that 7 is congruent to 4 mod 6. I'll put a big not congruent sign right here. 7 is not congruent to 4 mod 6. 7 is congruent to 1 mod 6, which is not the same thing. And the reason that this doesn't work, right, that we can't just go through and do this, is because the statements of this lemma are not satisfied. The greatest common divisor of 6 and 2, the thing that we're dividing through by, is not equal to 1. It's equal to 2. So if we go through and look at this lemma right here, we see that if A does not divide B times, if A does not divide C, then either A does not divide B times C, or the greatest common divisor of A and B is not equal to 1. So this is an explanation here as to why this is not working. And what's very neat, about what we've just shown is that we can actually go through and solve congruences. For certain values of the coefficients. So suppose we have a fixed A and B, and we want to solve for x in the equation A times x is congruent to B mod M for some M. Right? You cannot just divide through by A. Even if B is divisible by A. We need A and the modulus to be relatively prime to one another to be able to do this. So if A and M are relatively prime, or the greatest common divisor of A and M is equal to 1, then an inverse of A modulo M exists and is unique. We typically denote the inverse of A mod M as either A with a line over it or just A with a -1 in the exponent. But the -1 in the exponent should not be confused for any division at all, because it's not. And the proof of this is directly due to the Bayes-out theorem. So from the Bayes-out theorem, we have that there exists S and T integers such that S times A plus T times M is equal to the GCD of S and M, which is assumed to be 1. And if we take the modulus mod M of this equation, or the remainder of both sides of this equation upon division by M, what we're left with is that S times A mod M plus T times M mod M is equal to 1 mod M, which is just equal to 1. So T times N mod M is equal to 0, and we're left with S times A mod M is equal to 1. And what that means then is that S, or the Bayes-out coefficient of A, is directly the inverse of A. Oops, and this should be A here. I apologize for the typo. So this means that the Bayes-out coefficient of A, S, is the inverse of A modulo M. And this is just proving existence of this inverse, but part 2 would be a proof of uniqueness, which is relatively straightforward to go through and do. You just assume there exist two inverses, and you show that they have to be equal to one another. So let's say we want to go through and solve a given one of these linear congruences. Suppose we want to solve for x such that 3 times x is congruent to 4 modulo 7. The first thing that you need to check is that the GCD of 3 and 7 is equal to 1. And sure enough, it is equal to 1. So therefore, we can find an inverse of 3 mod 7 specifically that inverse is going to satisfy 3 times a bar is congruent to 1 mod 7. To figure out what this inverse is, a bar, it's relatively straightforward. We do a quick Euclidean algorithm. Specifically, when we do this, we see that 7 is equal to 2 times 3, or 6, plus 1, which means that 1 is equal to 7 minus 2 times 3, and you can clearly see that the base-out coefficient is -2, or the base-out coefficient of 3 is -2 in the linear combination expansion of the greatest common divisor using base-out's method. But this means directly that this base-out coefficient, as proved in the previous theorem, is the inverse of 3 mod 7. So -2 is this inverse. You can also see that because we're working modulo 7, -2 is congruent to 5 mod 7. So 5 is also a valid inverse for 3. And you can see that relatively clearly. Specifically, if you do 3 times 5, this is equal to 15. And 15 is congruent to 1 mod 7. So for this reason, a bar, the inverse of 3 mod 7, is equal to 5. Or I shouldn't say equal to, it's congruent to 5 mod 7. And so with this inverse, we can relatively quickly go through and solve this equation. If we look at this congruence and we multiply both sides, right, this congruence right here by this congruence right here, we have that a bar, or 5 times 3x is going to be congruent to 5 times 4 modulo 7, and 5 times 3 is 15, mod 7 is 1. This is 1 times x is congruent to 20 mod 7, or x is congruent to 6 mod 7, because 20 mod 7 is going to be 6. So we've effectively solved our congruence. We've solved for x. This idea can be extended to more complicated functions, more complicated ideas. Specifically, if you were to say add a value to ax, so you have ax plus some value c is congruent to b, you can use the same method to go through and solve for x, which is very, very impressive. What we could also do is consider systems of congruences, which are super important in many contexts. They arise in many, many different contexts. they're a basis for a method that can be used to perform arithmetic with large integers, and such systems of congruences can even be found as word puzzles in the writings of ancient Chinese and Hindu mathematicians dating back very, very far into history. For instance, in the 1st century, the Chinese mathematician Sun Tzu asked, there are certain things whose number is unknown. When divided by 3, the remainder is 2. When divided by 5, the remainder is 3. And when divided by 7, the remainder is 2. What will be the number of things? And this word puzzle can actually be translated very simply into a system of linear congruences. So solve for x, where x is congruent to 2 mod 3, x is congruent to 3 mod 2, and x is congruent to 2 mod 7. This is an example of a system of congruences. We're going to go through and we can go through directly now and solve this system by developing a theorem, and this is actually has a very a name that's named after this puzzle. It's called the Chinese remainder theorem, which is named after the Chinese heritage of problems involving systems of linear congruences. This states that when the moduli of a system of linear congruences are pairwise relatively prime, then there is a unique solution of the system modulo the product of each of the individual moduli. So if M1 through Mn are in Z plus, so they're positive integers, and they're pairwise relatively prime, which we defined earlier. Oh, and they have to be strictly greater than 1, so we'll just say strictly greater than 1, and they're pairwise relatively prime, and A1 through AN are arbitrary integers, then the system x equals A1, or x is congruent to A1 mod M1, x is congruent to A2 mod M2, all the way up to x is congruent to AN mod Mn, has a unique solution modulo M, where M is the product of all of the different moduluses. which means that there exists a solution x where x is between zero and strictly less than this value m, and all other solutions are congruent modulo m to the solution x. So the main way to go through and show this is to go through and directly prove this. And the idea here is that it directly relies on the definition of a sequence of values, call them capital MK, which is M divided by MK, or the ratio of this product of all of the different moduluses divided by the kth value of M, the kth modulus in our list. So we define MK to be this ratio for K from 1 to N, and we have a couple of results that are readily apparent. First off, this is going to be an integer because MK is a factor in M, and we also have that the greatest common divisor of MI in MK is equal to 1 because of the fact that we're assuming that all of these moduluses are pairwise relatively prime. This is when I is not equal to K. Therefore, it follows that the GCD of MI of MK with MK is also equal to 1. And this is because MK is a multiplication of all of the moduluses except for lowercase mk. I want to be really careful here to distinguish between uppercase mk and lowercase mk. Uppercase mk is the product of all of the moduluses except for mk, and because of the fact that mk has a GCD of 1 for each one of the moduluses where I is not equal to k, or mi is not equal to mk here, we have that this product, the GCD of this product with mk has to be equal to 1. And thus, by our inverse theorem, there exists a yk such that mk times yk is congruent to 1 mod mk. Or an inverse of this capital MK exists modulo mk, modulo lowercase mk. And to construct our solution then, x, what we're going to do is add up from the linear combination a1, m1 times y1 plus a2 m2 times y2 all the way up to an mn times yn. And it's relatively easy to go through and show that x is a simultaneous solution that we're looking for. We note that mj is congruent to 0 mod lowercase mk whenever j is not equal to k, and thus if we take the kth modulo of this x value, every term here is going to be 0 except for the kth term in this sum, because the terms are congruent to 0 mod mk. And because mk times yk is congruent to 1 mod mk, we then can clearly see that x is congruent to ak times mk times yk, which is congruent to mk mod mk for all the different values of k. And this is the ending point of this proof, because we've shown that this x satisfies each one of the congruences listed before directly. So this is cool because this allows us to directly go through and solve the system of congruences that Sun Tzu originally posed, as well as many other important systems of congruences in applications. Oh, and I just realized that I have a typo here. I sincerely apologize for this. This should be a 5, not a 2. And so going through and solving this is as simple as going through and saying, well, 3, 5, and 7 are all pairwise relatively prime. We form the modulus m 3 times 5 times 7, which is equal to 105. And we form capital M1, which is m over m1, or 5 times 7, which is 35. We form capital M2, which is going to be 21. And we form capital M3, which is going to be 15. And it's relatively easy to find the inverse of 35 modulo m1 modulo 3. m1 here is 3, m2 is 5, and m3 is 7. So y1, the inverse of 35 modulo 3 is going to be equal to 2, because 35 times 2 is 60, modulo 3 is going to be 1. this is because 2 times 35 is congruent to 2 times 2, which is congruent to 1 mod 3. Likewise, if we go through and find the inverse of 21 modulo 5, this is just going to be equal to 1, because 21 is itself modulo 5, just equal to 1. Remember, we're doing M2 modulo 5 here, and then M3 we're doing modulo 7. The inverse of 15 modulo 7 is also going to be 1. So in general, the correct way of going through and constructing a solution based on our direct proof is going to be that x is equal to a1 times m1 times y1 plus a2 times m2 times y2 plus a3 times m3 times y3. And so we know a1 is 2, a2 is 3, and a3 is 2. So our x is going to be equal to 2 times 35 times 1, or times 2, plus a2, which is 3, so 3 times 21 times 1 plus 2 times 15 times 1, which is exactly equal to 233. So our solution x is going to be x is congruent to 233 mod m, which is 105, or x is congruent to 23 mod 105. And this is the solution to Sun Tzu's word problem. Any integer that's congruent to 23 mod 105 is the smallest possible integer that is a simultaneous solution to these 3 linear congruences. Now, this is not necessarily the most quick method, the quickest method. A quicker method would be to use what's called back substitution to find all integers x, such that this is true. So I'll illustrate this back substitution method using these 3 equations as well. We call this equation 1, equation 2, and equation 3. We know that equation 1 means that there exists a k in the integers such that x is going to be equal to k times 3 plus 2. And if we substitute this into the congruence 2, so we do equation 2 or 1 into equation 2, this gives us that k times 3 plus 2 is congruent to 3 mod 5. It's the same thing as k times 3 is congruent to 1 mod 5, which means that k is the inverse of 3 mod 5, which is exists and is unique because 3 and 5 are relatively prime. And so k is equal to 2 because 2 times 3 is equal to 6, and 6 mod 5 is equal to 1. So this gives that k is congruent to 2 mod 5. So again, using the definition of congruences, we have that there must exist a p in the integers such that k is equal to p times 5 plus 2, which we can substitute back into the original equation. That is the original equation for x. Get that x is equal to p times 5 plus 2 times 3 plus 2. We're substituting this equation back into this equation right here, which is that x is equal to 15 times p plus 8. And lastly, what we do is substitute this into the third equation, which is going to be, this is solution for equation 1 and equation 2, and we substitute this into equation 3 and solve for p. So we have that. We do this, 15p plus 8 must be congruent to 2 mod 7. And so this can be solved relatively straightforward in noting that this means that 15 times p has to be congruent to negative 6 mod 7. And negative 6 mod 7 is 1. So 15p has to be equal to 1 mod 7, and we can solve for p by finding the inverse of 15 mod 7, which is just equal to 1, because 1 times 15 mod 7 is just equal to 1. So therefore p is congruent to 1 mod 7. And so x is just going to be equal to 15 times 1 plus 8, or 23, which is the same solution that we found using the direct method from our previous theorem. So you can use really any of these two methods, either of these two methods, backward substitution or our direct method, to understand how to solve these systems, but these are super important in applications. And so what I'll do is end the lecture with a proof that the prime factorization of any integer is unique. And this really just is based on a very short lemma, which completely relies on the previous theorem that I proved on the existence of a multiplicative inverse. and specifically the lemma on division of two integers by a if the greatest common divisor of a and b is 1, or a and b are relatively prime. So the lemma here is if p is prime and p divides a1 times an, where each ai is an integer, then p divides ai for some I. So p must divide at least one of the integers in the product. And the proof here is relatively straightforward. It just kind of uses the idea that p is prime and we assume that p divides the product a1 times an, or all the way up to an. Because p is prime, the greatest common divisor of p with any of the ai's is going to be equal to 1. And this is most easily shown using induction on n. So your base case here is if p is prime and p divides a1, then clearly we have that this holds because p divides a1 if p is prime and p divides a1 times a2, then because the GCD of p and ai is 1, we have that p divides a1 or p divides a2. And for some ai, we have that p has to divide ai. In the inductive hypothesis, then, is then that there exists some n such that the statement is true, in the inductive assumption, or I should say the inductive step, is to show that if it's true for some n, then for all n, statement n implies statement n plus 1. And this is a relatively good exercise for you to kind of think of how to go through and do it. So I'm not going to finish it, but it's a very good exercise. But with this lemma, then, we can go through and definitively show the uniqueness of the prime factorizations that we talked about earlier in the lecture. Specifically, you can do this using a proof by contradiction. This is the proof of the uniqueness of prime factorization. Mentioned before in earlier in the lecture, and I promised that I would go through and prove this. So we suppose that n can be written as the products of primes p1 through p, we'll say s, and that it can be written as product q1 all the way up to qt, where each pi and qj are ordered primes. So they're primes listed in the order of p1 less than or equal to p2 less than or equal to all the way up to ps, and q1 is less than or equal to q2, which is less than or equal to all the way up to qt. We can go through and divide common primes from both sides of this equation, and up until the point where we have a distinct number on both sides of the equation, specifically pi1 times pi2 all the way up to pis, and qj1, qj2 all the way up to qjt, where no prime occurs on both sides of the equation, and s and t are positive integers. And because no prime can divide another prime, we have a contradiction. This statement is a contradiction. And thus we're left to conclude that there can be at most one factorization of n into primes of non-decreasing order. So this is a very nice thing that we can use and is very, very useful. Now, there are a lot of applications and other things that you can do with modular arithmetic, and specifically with some of the things that we talked about in this chapter, such as computer arithmetic with large numbers. There's a number of very important theorems that show up, such as Fermat's little theorem, the concept of pseudo-primes, which leads to the definition of Carmichael numbers, and finally to solving for what are called primitive roots and discrete logarithms. Right? All of these things have very interesting applications in number theory, and also to many of the applications of modular arithmetic to solving problems, of which there are many. Hashing functions, pseudo-random numbers, we talked about in detail when we talked about the linear congrugational generator, check digits, check bits, ISBNs, right? There's a whole bunch of very important applications, but the application that we're going to focus on in the next lecture is to what's called RSA cryptography. So this is going to be the next big thing that we'll talk about. And what I will do is just write down Fermat's little theorem without proof, because this is something that will come up and we might prove a little bit later on. So Fermat's level theorem says that if P is prime and A is an integer not divisible by P, then A to the P minus 1 is congruent to 1 mod P. Furthermore, for all integers A to the P is congruent to A mod P. Thank you so much for tuning into the lecture today. I hope you learned something and you had a fantastic day.